Here are some kids playing freeze dance, sometimes called musical statues. In this video, we'll solve a probability puzzle involving freeze dance. Near the end, we'll even see a connection to the movie Mean Girls. Our story begins with a paper that Joel Spencer and I wrote. Joel is an expert on probabilistic methods. I had the pleasure of being Joel's colleague at New York University for 10 years. These photos are from that time, with Joel on the left. We wrote a handful of papers together. One of our papers was on random graphs. Near the start of that paper, we needed to solve a probability puzzle. We posed that puzzle in terms of a random dance. In this video, I'll tell you about that dance puzzle and its surprising solution. Have you ever played freeze dance? Some music is turned on and then you have to start dancing. At some point, the music is suddenly stopped. At that moment, you have to stop dancing and freeze in position, like a statue. If you don't immediately freeze, then you're eliminated from the game. Let's see an example. In this example, we have 20 players. We'll name them A, B, C, and so on through T. Let's see what can happen after one round of freeze dance. The players with a red X are eliminated because they didn't freeze right away. The players with a green check mark are still in. Of the 20 original players, 10 are still in the game. What happens next? We'll play another round. Only the players still in the game will dance. Let's see the outcome of the second round. Of the 10 remaining players, 7 dropped out and only 3 remain, A, F, and S. Let's continue with the third round. A dropped out, so only 2 players remain, F and S. Let's see the fourth round. Oh no! Both players dropped out. What does that mean? It means nobody won. We don't have a winner. So in freeze dance, sometimes you'll have a winner, a unique winner, and sometimes you won't. The question we'll pose is, how likely is it that we will have a winner? A question in the form, how likely, is a probability question. To make that question precise, we need a random model, some assumptions on how the game will proceed. And here is our random model for freeze dance. We'll start with n players, where n can be any whole number. At every round, each player has a 50% chance of continuing to the next round and a 50% chance of dropping out. Each player is independent of the others, meaning whether some players drop out or not doesn't influence whether another player drops out. Furthermore, the rounds are independent, meaning that the outcomes of one round aren't influenced by the outcomes of another round. Finally, the game will continue until there are 0 or 1 players remaining. If exactly 1 player remains, then that person is the winner. Otherwise, there is no winner. Great, we have a precise random model. We can now try to figure out how likely it is that we will have a winner. Let's give a name to the winner probability. We'll say that P of n is the probability that we will eventually have a winner in freeze dance, given that we started with n players. We'll try to determine P of n for every whole number n. Let's start with small n. What's the fewest number of players? We could have 0 players. What is P of 0? It's 0. With 0 players, nobody can win, so the probability of a winner is 0. Okay, let's move up a notch. Suppose we have 1 player. What is P of 1? It's 1. With only 1 player, that player automatically wins, so the probability of a winner is 1. Fine, let's move up again. Suppose we have 2 players. We'll call them A and B. Before we jump in, what do you think is the probability that we'll have a winner with 2 players? Is it 1/2, less than 1/2, or more than 1/2? Let's find out. What can happen in the first round? There are 4 possible cases. Here are the 4 cases. In the leftmost case, both A and B survive. In the second case, A survives but B doesn't. The third case is the opposite. In the fourth case, both A and B drop out. Each of the 4 cases is equally likely, having probability 1/4. All right, let's use these 4 cases to compute P of 2. Here we have expressed P of 2 in terms of the 4 cases. There are 4 terms in the sum, 1 for each case. The good news is that we know P of 0 and P of 1 already, so we can substitute their values in to simplify. We have an equation expressing p of 2 in terms of itself. Fortunately, it's a linear equation, so we can solve it. We find that p of 2 is 2/3. The probability of having a winner with 2 players is 2/3. Does that surprise you? Okay, let's bump up to one more player. We now have 3 players, A, B, and C. Take a guess at the probability of having a winner. There are 8 possible cases for the first round. I've grouped the 8 cases into 4 buckets, according to how many players survive the first round. The leftmost bucket is the case when all 3 players survive. The second bucket has 3 cases, when exactly 2 players survive. The third bucket also has 3 cases, when exactly 1 player survives. The fourth and final bucket is the case when all 3 players drop out. Do you see how to use these buckets to compute p of 3 in the same way we computed p of 2? Here we've expressed p of 3 in terms of the 4 buckets. We already know the values of p of 0, p of 1, and p of 2, so we can substitute their values in and simplify. Great! We've expressed p of 3 in terms of itself, so we can solve. We find p of 3 is 5/7, about 71%. Here we developed an equation that expressed p of 3 in terms of the previous values of p. Such an equation is called a recurrence. In the same way, we can create a recurrence for more players. That way we can compute p of n for any n. Let's compute a few more probabilities. Here we'll compute the values of p of 4, p of 5, and so on through p of 9. As before, we'll develop a recurrence for each and solve. Here are the answers. P of 4, P of 5, 6, 7, 8, and 9. We have some wild fractions here, with numerators and denominators in the millions. To see what's going on, let's look at their decimal equivalents. Here are the decimals for p of 0 through p of 9. Do you think these probabilities are approaching a specific number? It looks like the probabilities are headed toward 0.72 something, around 72%. To increase our confidence, let's look at data with many more players. By the way, take a guess at the world record for the most number of players in a game of freeze dance. According to Guinness World Records, the current record is 1,308 players. This photo is from that group in Florida. Okay, let's see how the probabilities change with such a large number of players. Here we'll list the probabilities for p of 100, p of 200, and so on through p of 2000. Let's look at the probabilities on the left. They're all 0.7213 something. Let's look at the probabilities on the right. Same thing. Does it look like the probabilities are converging to a particular constant? Let's see the data in visual form. Here is a plot of the values of p. The horizontal axis is the value of n, the number of players. The vertical axis is the value of p of n. Note that the vertical axis is only going from 0.721 to 0.722 because all the probabilities are in that narrow interval, at least for more than 8 players. Does it look like the values of p of n are heading toward a certain limit? To me, it looks like the values are heading toward a number just above 0.7213. For some folks, this numerical and visual data is convincing enough to move on to the next problem. But for mathematicians, like myself, we haven't proved anything yet. Let's see if we can prove that the limit exists. Okay, for the rest of the video, we're going to try to figure out the limit of p of n as n heads to infinity. How will we do so? First, we'll try to develop an explicit formula for p of n. By an explicit formula, I mean something like this. We'll try to write p of n as an expression involving only n. Before, we developed a recurrence expressing p of n in terms of previous values of p. Here we'll look for a formula that doesn't involve previous values of p. How will we develop such a formula? Let's use a helpful trick. In freeze dance, if there's exactly 1 player remaining, then that player is declared the winner and the game ends. Instead, imagine that we keep going until the winner is also eliminated. That might seem like a weird thing to do, but it's a useful idea in many probability problems. Anytime you are faced with a thorny probability question, consider the idea of adding such fictional play. Let's see an example. Again, we have our 20 players. Let's play a round of freeze dance. Now there are 10 players remaining. Let's try a second round. Now there are 3 players. Next, the third round. Now there are 2 players remaining, F and S. Next, the fourth round. Now S has been eliminated, so we have found our winner F after 4 rounds. Still, we'll imagine keep going on. Let's try a 5th round. F survives. And a 6th round? Again, F survives. Next, a 7th round. Finally, F messed up. F is still the winner, but we can count how many rounds F lasted. The winner F survived for 6 rounds before dropping out in the final round. So, how are we going to use that fictional play? Here's our strategy. When faced with a difficult probability question, consider dividing the problem into cases. Remember that P of n is the probability that we'll have a winner among n players. What cases can we break the problem into? Well, we can see how many rounds the winner lasted using our fictional play. The winner can survive exactly 0 rounds, 1 round, 2 rounds, and so on. We'll compute the probability of having a winner who survived a given number of rounds, and then add up the probabilities. Okay, we need a formula for the probability of having a winner who survives for exactly r rounds, where r is a given whole number. How can we do that? Here's a table of what might happen in a game of freeze dance. We've listed the n players on top. We've listed the rounds on the left. We want a winner who survives for exactly r rounds. We don't know who the winner will be, so let's say it's the last player, player n, and at the end we'll multiply the probability by n to account for the n possible winners. For player n to survive for exactly r rounds, it must survive rounds 1, 2, and so on up to r, and then drop out at round r plus 1. That's why we've shown green check marks in rounds 1 through r, and finally a red X in round r plus 1. What about another player, say player 1? Player 1 was not the winner, so player 1 must have an X somewhere in rounds 1 through r. The same is true for players 2 and so on through player n minus 1. What's the probability that the table looks that way? Let's compute. Here are the probabilities of each column. For example, let's look at the last column, the one for player n, the supposed winner. What's the probability that the last column looks as it does? Player n has probability 1/2 of behaving in a certain way in a given round, and there are r plus 1 rounds. So the probability of player n behaving correctly is 1/2 to the power r plus 1. That's 1 over 2 to the power r plus 1, as we have written. What about another player, such as player 1? Player 1 must not have survived for the first r rounds. Let's look at the complementary probability. The probability that player 1 survived for r rounds is 1/2 to the r. That's 1 over 2 to the r. Therefore, the probability that player 1 doesn't survive for r rounds is 1 minus 1 over 2 to the r. That's what we've written. What we've said here for player 1 goes for players 2 through n minus 1, too. Each has probability 1 minus 1 over 2 to the r of dropping out by round r. All right, we've computed the probabilities for each of the players. Since the players are independent, we can multiply these probabilities to get the final probability of having a winner who survives for exactly r rounds. Here's what we get. Do you see where all the factors in this expression come from? The factor 2 to the power r plus 1 comes from player n. The factor 1 minus 1 over 2 to the r, all raised to the power n minus 1, comes from players 1 through n minus 1. And what about the factor of n? Remember, we had n choices for whom the winner could be, so we have to multiply by n. Great! We've developed a formula for the probability of having a winner who survives for exactly r rounds. We can use that to develop a formula for P of n itself. Remember when we talked about breaking our probability into cases? We had the sum you see here. we now have a formula for the inner probability. So this is the formula for P of n that we wanted. Hooray! This formula is exact, but not easy to work with as is, so we'll make some approximations to simplify it. Here again is our exact formula. We'll replace the exponent n-1 with n. That doesn't change the value by much, right? Next, we use the fact that a number of the form 1 minus x can be approximated by e to the minus x whenever x is small. Here, e is the base of natural logarithms, around 2.718. Finally, instead of having r go from 0 to infinity, we'll allow r to go from negative infinity to positive infinity. That seems like a weird move, but it makes our sum more symmetric. That change is only exponentially small. This final sum is important enough that we'll give it a name. Let's call it Q of n. The three approximations here are good enough that the limiting behavior of Q is the same as the limiting behavior of P. So let's understand Q better. Okay, we'll list the first few values of Q. Here they are. What do you notice? Each of the numbers starts off as 0.7213, but after that, some numbers look identical while others look different. To see what's going on, let's color code the numbers. The numbers in red appear to be the same: Q of 1, Q of 2, Q of 4, and Q of 8. The numbers in green appear to be the same: Q of 3 and Q of 6. What's going on? It looks like doubling n doesn't change the value of Q. And that's exactly right. Q has a kind of periodic behavior. Namely, Q of 2n and Q of n are the same. How will we prove this claim? The proof is just 4 lines. First, stare at this formula for Q. We'll plug in 2n for n. Note the appearance of 2n in 2 places on the right. Second, we'll simplify by canceling some factors of 2. Third, our key step, will shift the index of summation by 1. Namely, let k be r minus 1. In other words, replace r by k plus 1. Because r goes from minus infinity to positive infinity, so does k, right? That's why we made the sum doubly infinite. Finally, if you stare at the final expression, you'll see that it's exactly Q of n. The only difference is that the variable is named k instead of r, but the variable name doesn't matter. So we've proved the claim. This periodic behavior will be quite useful to us. Let's see how. Our original goal was to figure out the limit of P of n. Instead of going there directly, let's assume that n is a power of 2. We'll calculate the limit on that subsequence. All right, we're trying to calculate the limit of this subsequence. Because P and Q are so close to each other, we can replace P by Q in this limit. By our periodic property, Q at a power of 2 is what? It's Q of 1. So the limit is Q of 1. And we've already computed Q of 1 numerically. It's 0.721352 something. That's great. We finally figured out some kind of limit. We determined the limit on powers of 2. Do you see how the same idea works on any doubling sequence? Let's try another such sequence. Here we'll look at numbers of the form 3 times a power of 2. For example, 3, 6, 12, and so on. What's the limit of P of n as n goes through these numbers? We can use the same approach. Again, we replace P with Q. Q at 3 times a power of 2 is what? By the periodic property, it's Q of 3. And we've computed Q of 3 numerically. It's 0.721346 something. We've computed the limit on 2 subsequences. Let's compare the 2 limits. On the powers of 2, the limit of P of n is 0.721352 something. On 3 times the powers of 2, the limit of P of n is another number. So what's the limit of P of n itself? Is it the first number, the second number, or something else? Well, to quote the movie Mean Girls, The limit does not exist. Instead, the probability is oscillating, never approaching one single number. Let's see a graph. Here is a precise plot of P of n. Previously, we had seen another plot of P of n, but now we've blown up the plot. The vertical axis is precise to 5 decimal places. Now we can see that P is oscillating without converging to one number. Our broader lesson here is don't be too convinced by our initial data. We may need to look more closely to see the underlying pattern. In math, proof is the gold standard. Finally, I find it fascinating that we combine different techniques and concepts to solve this one puzzle on freeze dance. Here I've listed 11 of the concepts, from recurrence equations to infinite series and periodic functions, which touched on so many different concepts. In the video description, I've provided links to a few references on this problem. Thanks for watching.